Hello. In this video we'll be doing some practice problems involving light and spectroscopy. And by spectroscopy what I'm referring to is absorption and emission. So let's just jump right into it and look at question number 1. So question number 1 asks, a red laser emits a beam of light with a wavelength of 635 nanometers. What is the energy per photon of this light? What is the frequency? So we'll start with the first part of the question first. So the first question is, what is the energy per photon of this light? So that lets me know that we're going to need to reach for an equation up here, and I've given you some equations and constants that will be very helpful in these practice problems. And we'll need to look for something that we can use. So in the question we're given wavelength, which is represented by the Greek letter lambda, which is this guy here. He looks kind of like a drunk K. But it's the Greek letter lambda, and it means wavelength. So this equation right here looks like a good place to go, because it gives us what we need, and that's wavelength. We have a wavelength, so it looks like it would be pretty convenient to plug it in to where it is. And that's sort of the thing that you'll want to do when you're looking for equations to use in your problems and how to solve your problems. Use sort of your Occam's razor skills. So look for the simplest equation that gives you the most of what you need to get to the answer you want. That might sound a little weird, but basically look for the stuff where you have to do the least amount of work. Usually that'll be the best equation to use in my opinion. Because h and c are both constants. We have Planck's constant and the speed of light. So we just plug those in. And wavelength, well, we've got a wavelength, so we can just sneak that sucker right in there and plug it in. And our problem's solved. All we have to do is a little bit of math, which really just means a little bit of plugging into a calculator. So, pretty simple question to solve for. So we'll be using this equation here. Okay, so I've got everything set up in the equation that I think we need. I've got Planck's constant plugged in, I've got the speed of light plugged in, and I've got our wavelength plugged in. But take just a second and look over what I've done here and see if you can find a problem. Look specifically at the wavelength and see if you can tell what the problem is with that wavelength. If you'll notice, I've got it in nanometers, which is what it was in the question. The question gave it to us as nanometers, so I simply put it in as nanometers. This is a common thing I've seen students do in the past. I've seen them just think, okay, I've got to plug in wavelength. I've got my wavelength. I'll just plug in what I've got. The problem with that is that the units here, nanometers, do not match up with the units up here. Remember, the units for the speed of light are meters per second. So we cannot have our wavelength in nanometers. We have to have our wavelength in meters. Luckily, there's a pretty straightforward way to convert from nanometers to meters. And that's by using this little conversion factor over here. So just a very quick one-step dimensional analysis. The conversion that you'll need to know is that 1 meter is equal to 1 times 10 to the 9th nanometers. And that's because a nanometer is 1 billionth of a meter. So 1 times 10 to the 9th, divide those two, and that will give you your answer in meters. There's also a shortcut to convert this, and I'll try to show you that at the end of the video. But, you know, if shortcuts aren't really your thing and you're more about always getting the right answer, I would probably stick to the conversion factor. And that's right here. And you'll get 6.35 times 10 to the negative 7th meters. And we'll use this number here to plug in for here. So we'll just swap those out, and then we'll move on. Okay, so I've just done a little switcheroo, swapping out the nanometers for the meters. So now all of our units match up, they sync up nicely, we are ready to go. So what I would recommend doing is I would pause the video, work this out yourself in your calculator, see what answer you get, and then compare the answer you get with the one I show after you unpause the video and see what I put. So take a second, try this one out. Okay, so this is the answer, and so hopefully this matches what you got, and if it doesn't, go back and see what you did wrong. I'm willing to bet it was something to do with a calculator mistake. You want to know my solution to all calculator mistakes? Use a bunch of parentheses. So if you use a bunch of parentheses, it'll help alleviate the calculator errors that might come up. So this is the answer you should get. So that's the energy associated with our photon of light. So that answers the first part of the question. Now we have to address the second part, which is asking us to calculate the frequency. And for the frequency, we're actually going to have to use an equation that I sort of left out of the equations I gave you at the top, but it's one that's kind of implied. So here is our equation for frequency. And remember, frequency is represented by the Greek letter nu, which looks kind of like a curvy V, but it's known as nu. And that's equal to the speed of light over the wavelength, which is lambda. So we can use this here, which we have both components of, to calculate for the frequency. Although technically you could also use this equation up here as well. So up to you. I'll be using this one just for illustrative purposes. Okay, so here's the setup for our frequency equation. So we've got the speed of light on top, and we've got our wavelength on the bottom. But like I said, if you wanted to, you could also use this equation up here, where you can use Planck's constant and the energy that we just calculated to solve for frequency. So, like I said, up to you which one you want to use. But just for variety's sake, I'm using the technical frequency equation. So I'll give you a second. Feel free to go ahead and pause the video, do this, and compare your answer with mine after you unpause. So here you go. So this should be your answer here. 4.72 times 10 to the 14th reciprocal seconds. And what I'm going to emphasize is the units. So reciprocal seconds here and joules per photon up here. Please always make sure to include your units, because if you're taking a quiz or a test, you will lose points, because if you do not include units, you do not have a complete answer. Numbers without units in chemistry are completely meaningless. You have to have units attached to your answers if you don't want to lose easy points. I'm telling you, easy points. So make sure you include those in your answers. So that wraps up question 1, and we'll move on to question 2, which deals with spectroscopy and the Bohr equation. So here is question 2. So what is the wavelength of light in nanometers that is required to move an electron from n equals 2 to n equals 6 in the hydrogen atom? So let me draw you a quick visual of what this is going to look like. So here's what we have. We have an electron on the second energy level, and a photon comes along and gives its energy to that electron, and that electron bumps up from the second energy level and goes all the way up to the 6th energy level. Now, think, what process is this? Is this absorption or emission? Well, hopefully you said absorption, because that's exactly what this is. Remember, when you go up energy levels and you take on the energy of a photon, you're absorbing. You have the process of absorption. So that's what this is right here. And there's a way we can calculate this mathematically using the combination of these two equations over here. This is called the delta E process equation, where you take the energy of a final state minus the energy of an initial state. So in this system, our initial state is n equals 2, and our final state is n equals 6. And we're going to use that in the context of this, which we talked about before, is the Bohr equation, and we're going to substitute this in for our two energy levels. And we're going to plug this Bohr equation into this guy up here, where we'll take our final state, which is where n equals 6, and subtract it from our initial state, which is n equals 2. Which, if that sounds a little confusing, it might, but I'm going to write it out, and hopefully it makes a lot more sense when you see it written out in mathematic form. So there you go. So that's what the setup is going to look like. So we have our final state here, where we're at the 6th energy level, because that's where we ended up at. That's our final state, which is the EF. And we're going to subtract that from the initial state, which is when we started, which was the 2nd energy level. So when we do all this math, we're going to end up calculating the energy of the photon of light that did all this to begin with. And from that energy, we can then calculate the wavelength. So I'm going to give you a few seconds. Feel free to go ahead and pause the video, work out this math up here. Definitely be mindful of this subtraction that's taking place here. Work this out, and then see what your answer is, see if it matches mine, and then we'll go from there. Okay, so you should have gotten something right around 4.84 times 10 to the negative 19th joules. So if you didn't get this, go back and look at your math. Make sure you used parentheses, and make sure you took into account this negative sign here, this minus sign. So this should be your answer for the energy of the photon that moved that electron. So that's the energy, but we wanted to find the wavelength. So what we're going to do is we're going to use, that's right, this equation again, but we're going to use it kind of backwards from how we used it in the first question. Because in the first question, if you remember, we calculated the energy. Here we're going to calculate the wavelength, so we're going to focus on lambda. So you want to rearrange that equation in order to solve for lambda instead of E. So I'm going to let you rearrange that really quick and see what it looks like and compare it to mine. So go ahead and pause the video. So there you go. So there's our rearranged equation, where we arranged it to solve for lambda, which is wavelength. So wavelength is equal to the Planck constant times the speed of light divided by the energy of the photon. And we just solved for the energy of the photon. That's this number here. And we know the Planck number, and we know the speed of light. So just plug all those together, and this is what that will look like. So that's your setup. So we've got the Planck constant times the speed of light divided by our energy of our photon, and this will give you the wavelength in meters. So again, pause the video, work this out, and see what you get for your answer. Compare it to mine. So here's the answer that you should get. So 4.11 times 10 to the negative 7th meters. There's only one problem left, though. The question asked for nanometers, and our answer here is in meters. So we're going to need to do one last thing. We're going to need to convert this meter answer into nanometers. Now you can of course use the conversion factor of 1 times 10 to the 9th nanometers is equal to 1 meter. Or you can use a little shortcut. So the shortcut is going to involve taking this decimal place here and moving it twice. So move that decimal 2 times, and we're going to knock off this scientific notation. So move the decimal twice, knock off the scientific notation. And what you'll be left with is 411 nanometers. And that's the shortcut way. So I'll also put up the conversion way in case you wanted to do that. So here is that conversion factor in case you wanted it, and that will give you the same answer as using the shortcut. So whichever way works best for you. If the shortcut confuses you, by all means don't use it. Use the conversion factor because the conversion factor will always be right. The shortcut only works in certain circumstances, so I wouldn't rely on it. So if you want to rely on anything, rely on the conversion factor. And that will give you 411 nanometers, which is the answer to question 2. So hopefully this gave you some good practice with these questions, how they're asked, how you can work through them. Hopefully it helped make a little more sense out of all this math that's going on.